Hello, welcome to the first episode of Math with Haas. Now, Math with Haas, if you had watched a welcome video, which I guess would technically be the first video, this is the first video with math in it. So, Math with Haas. We are going to start with Precalculus. I called this episode 1.1 because we're going to start off with Precalculus Season 1, and this is Video 1. Our topic for Season 1 is exponential and logarithmic functions. Now, a lot of pre-calculus classes, they'll start with a review of algebra, and they'll explore linear equations, polynomials, rational functions. I'm going to bracket that aside and save that for a series on algebra if I ever do that, simply because I find that I guess it's not as intriguing to me as exponential and logarithmic functions. In general, with my students, they've already done lots of drills on those topics, and so I like to start with something new. And this something new is usually exponential and logarithmic functions. So you're probably wondering, what is an exponential or a logarithmic function? What we'll do is first explore the notion of exponential functions, and then tie in logarithms from the idea of exponential functions. So let's go ahead and start with our exponential functions here. So a pre-calculus student should have already a solid foundation of algebra skills with they've already spent a lot of time with linear functions and whatnot. So what we want to do is think about a nice concrete example. What makes exponential functions different from linear? So what we'll do is consider a nice concrete example. So linear functions have, when they grow, if you imagine like a number of companies in a store, for example, a linear will have a nice line like that, and it's constant. If I could draw straighter, it would be nice and straight, though I guess I could have just used a ruler. Whereas exponential is going to look something like this, where it just shoots straight up really high. So because of how poorly I drew this slide, it might make you think, well, maybe it looks like a polynomial, but we'll see in a moment. So let's consider two companies, Company A, Company B. So what we're going to do is look at the difference between linear and exponential in terms of growth with two companies. So each company has 100 stores. So, and each company has decided they're going to focus on expansion. So Company A is going to add 50 stores per year, while Company B is going to increase the number of stores by 50% per year. Okay, so each is starting with the same amount of stores, but one is going to increase their number of stores, or A will increase their number of stores 50 stores per year. Company B is going to increase their number of stores by 50%. So we can make a table of values. Company A will have, so let's see here. We'll use time, a t for time, since we are considering years, and here's number of stores. So at year 0 we have 100 stores. At T1 what we have is 100 stores, but we're going to add 50 to it, so that's 150 stores. 2 years we'll have 200, and so on. So what makes Company B different? So we could set up our table of values here. Number of stores. So when we're just starting out, we have our 100 stores. Now, 50% of 100 is 50. We think, what is half of 100? Well, that's just 50. So 1 year in, we have also 150 stores. But now, for year 2, since we have 150 stores, if we think 150, what's half of that? Well, that is 75. So we'll have 150 stores, but we're going to add 75 more. So now we have 225 stores. And 3 years later, so 125, right? 225, 5 by 2, 112.5. So now we're going to have 337 stores in 3 years. So in just 2 years, Company B has already surpassed Company A in a number of stores, and within 3 years has already exceeded what Company A would have in 4 years, in fact more like 4.5 years. So we can see it does not take much time at all for the growth of Company B to exceed a linear growth model as demonstrated with Company A. So this right here, Company B, exemplifies exponential growth. Now, what we want to do is think about how can we come up with an equation for this. Company A is fairly easy. We know that if we have a function y equals mx plus b, we know the y-intercept is just 100, and the slope, well, we're just adding 50 stores a year. So we want to take whatever our time value is, multiply by 50. So this is just going to be 50x plus 100. But what is the equation for Company B here? To do that, we have to be a little ingenious about this. So what we'll do is think about, what if we were to rewrite this? So we have 100 plus 0.5 times 100 is equal to 150. 150 plus 0.5 times 150 is equal to 225. Now this here, let's see, so we're going to just write this out. So 225, so 225 plus 0.5 times 225 is equal to 337.5. Now what we need to identify here is a pattern. So we have 100 here, and we have a 100 right here. And similar cases to 150 to 225. So we can rethink this as there's one whole copy plus half a copy, so that's 1 plus a half times 100. Similarly, we have a whole plus a half copy, so we can think of this as 1 plus a half times 150. So this was equal to 150, this was equal to 225. We can do something similar here. 1 plus a half times 225 must equal 337.5. Oops. Got too close to the edge there. Alright. So now we can play with this pattern here. So we said that 150 is equal to all of this. So what if we put it in right here? Well then 225 is going to equal 1 plus 0.5 times 1 plus 0.5 times 100. Or just 1 plus 0.5 squared times 100. Now 225 here, since this is equal to this, notice it is right here. So we can do the same thing. 337.5 is equal to 1 plus 0.5 this term here is coming from right here. And then we have our term from the blue, 1 plus 0.5 squared times 100. In other words, 337 can be rewritten, or 337.5 I should say, as 1 plus a half cubed times 100. So now we have a table of values here. So we have 0. When t is 0, we have 100. When t is 1, we have 1 plus 0.5 times 100. At 2, we have 1 plus 0.5 squared times 100. And when t was 3, that was 1 plus 0.5 cubed times 100. Where are these values coming from? Remember, this value here is just 150. This is 225 and 337, as we showed right here. Now, we can start introducing some variables. So y equals, so notice that we have 100, 100, 100, 100. So we can just call that the initial amount, right? The company B had 100 stores initially, so we'll just call that initial amount. We'll use a letter A. Now, we said company A was increasing by 50%. That 50% has come into play all over here. So we can make a equation where it's 1 plus a rate, r. Now, this 1 plus r, you might be wondering, where is it at here? But if we remember, anything to the 0th power is just a 1. Notice it is right here also. And now we have our third pattern more visibly, namely right here. So when t is 0, we have a 0 exponent. When t is 1, we have a 1. So right here is our exponent t. This gives us our first taste of what an exponential function looks like. So a would be, we could think the starting population, the initial amount of stuff. We could also think beginning amount. R is going to equal the rate of, now we want to talk about growth, but it could also be decayed. So instead of increasing, company B could have been decreasing at 50 stores per, or 50% of stores per year, for example. That would require a negative R. And then we have T, where in the context of our story it was time. In fact, usually when it comes to applied problems it is time, but for now we just say it's the independent variable. But I could probably work on my handwriting. There we go. Independent variable. And this is usually time. Alright. So this is our first equation for exponential growth. And we could put the constants in and get what company B looked like. So if we zoom out a little bit, okay, zoom out a lot. So right here was company A. Company B, we start out with 100 stores, so that would be our A. Our growth was 50%, so that's 0.5, and then we would just have a T. We could have used an X. We could have used an X or T. It doesn't matter. So this illustrates the difference between our two types of growth, the exponential and logarithm, or the exponential and the linear growth. Alright. So this first video gives us an idea of what is a linear or an exponential function, what kind does it look like. Now, next time we'll have to look at, I guess we'll work on generalizing our result and applying this to some problems. Alright, thank you for watching this first episode of Math with Haas. If you've enjoyed this video, please stick around, subscribe, support us on Patreon. Thank you, and join us next time.